Um,
Yeah, that'd be quite a quite a lecture. All
yeah,
right.
great. Okay, so thanks a lot. Today, Dan Daly, who's a chip architect at Intel, is here to talk to us a little bit about FlexPipe. So, thanks for joining us, Dan.
No problem.
I wanted to ask first, just starting off, like what are the origins of the FlexPipe project, and what sort of what demands were kind of driving this new chipset? Were they requests from vendors or operators, new applications, something else? Where did this come about?
Well, I think the flexibility was designed uh, given the size of our team. So we were a startup at the time, and we had a lot of requests from different places. We didn't feel like we could, you know, build a chip that had the perfect pipeline for everybody. So we took a lot of the different requests that we had, and we built a pipeline that was flexible, so that we could evolve it over time, and that allowed us to kind of react to new protocols as they came up, as sort of SDN became to mature, and new things kind of popped up, and it was straightforward for us to go and take our pipeline and reprogram it to do the new things that you needed. So from that perspective, it was successful. We needed to be we needed to be flexible in order to handle this a lot of these changes that were happening in the network. And then when you put something in even sort of an established environment, someone will come up with something new that they need, or if it's an embedded device and there's some sort of tagging that's happening inside the system, it's really good to be able to programmably parse any sort of packet and programmably modify the packet in arbitrary ways to because you're essentially the glue between multiple endpoints, and so if you just want to get out of the way and make sure all the pieces fit together.
Yeah, that's cool. I guess so. Yeah, you saw a need for this, I guess, and then you sort of wanted. You said you wanted to design a chip that was as flexible as as flexible as you could possibly make it, or
Right.
given what you were seeing. I guess that brings me to another question. It's just like it sounds like you were just didn't know really what was out there, and you just sort of, or you didn't know what was coming, I guess you could say, and you just wanted to make it super flexible. But at some point you had to decide on some set of actions. So where did you decide to draw the line, or how did you basically come to the decisions on the sets of actions that you would put in your processor?
Right. Well, we had a lot of experience from our previous design, the Bali FM 4000 chip. So we had a sort of a baseline understanding of what people were doing with these chips, and so we took that and expanded on it, understood some of the requests that we had, and added a couple things in for good measure, just to make sure that we'd have that extra flexibility and headroom. But if you think about just like the primitives of what a chip has to do, it's not that large of a set. There are some curveballs like being able to do IP checksums and putting the hash of a packet into the header, like you end up needing for VXLAN. Those are the types of things that you kind of put in there, understanding that maybe someone will want, and then 6 months down the line, something does pop up like VXLAN that needs both of those features, and you're happy that you had them. So I would say the set of things is not that large. You just have to be able to combine them in an arbitrary way.
Yeah, so when you saw, I mean, you mentioned VXLAN, and you also pointed out that it didn't exist when you first designed the chip. And it sounds like in that case you were you made I guess the right decisions, in that you were sort of the sets of features that you and actions that you had on the chip were able to handle that
Right.
set of functions. But are you seeing now that there are things that you didn't anticipate, such that like what is the next version of FlexPipe going to look like? Do you think it's going to include more things, or maybe less things? Right? Maybe it's more specific because you have a better idea of maybe things you didn't need, or do you think you left things out?
Well, I would say I think as we evolve the architecture, we really want to focus on being able to scale and this might just come from a different perspective as being part of Intel, but the ability to interconnect large numbers of processors is really important for us, and we sort of have the a new type of relationship with what's going on that processor because of the things that we're doing with software data planes. So it just gives us a little bit more perspective, and we have a lot more of that information that we didn't have before in terms of what are the types of things you want to do, and maybe we can be a little bit more focused. But you still want that flexibility. You still need to, there's going to be new innovations you can't really predict. So it's good to have that tool set. But being an interconnect for these types of data centers, that's really the focus. You have to really get that right, and then the flexibility is sort of a feature on top of that. So I think that's how sort of FlexPipe will evolve. It's a fairly complete set of actions and primitives, and just take it on to the next generation after that.
Yeah, you mentioned software a little bit and sort of integration with software. I think that's kind of an interesting discussion that's circling around in various ways, and sort of what functions belong in software versus in hardware. I wonder if you could talk just a little bit, just generally about that. I have some specific questions, but what types of things should be placed in on a host or on a server that's sitting in the network versus on the switch itself. Intel obviously does both now. So what do you think about that?
Well, I think not just for Intel, but for everyone, ideally, you'd want everything to be totally flexible, totally programmable, everything in software. So, that's sort of the nirvana. Let's put everything into a software pipeline. And
do you think it's going to happen? I mean, do you think do you think that software will eventually catch up, if you will, or do you think that there's always going to be some kind of gap?
Well, I mean, right now the gap is pretty large. So if you tried to do a switch on one processor, it's orders of magnitude depending on the type of software that you use. But the processors are getting faster every year, and we're figuring out better ways to distribute types of workloads on these processors, so you can combine them together in different ways. So I think one of the obvious things that happened in SDN is it sort of evolved from starting on the hardware. This is how you software define a network instead of having that run on an ASIC. It immediately jumped over to the host, because that's where you could do all this really interesting stuff. You didn't have to wait for the ASICs to catch up. So given that understanding, you have to go back to the network and say, okay, well, this is going to happen. The hosts are getting smarter. We can move more and more of the network to the edge. What is the role of the network at that point? Does it still need all of that flexibility that we want it to have? Does its role change? Does it get marginalized completely? And that's sort of the balance that you have to find out. And a lot of different customers that we have are on different ends of the spectrum, and they're all still Intel customers. So.
Mm-hmm. So one possible way you might see that going is there's really complex tagging and manipulation and processing at the end hosts, but then the switches have relatively simple sets of operations that they do based on tags that exist on packets or something like that. Is that kind of
right.
where you see things going?
That's one possibility. Yeah, there is still a lot of value in the fabric. You still have to be able to. There's a lot of value in trying to engineer that fabric end to end. But there might be a lot of things that certainly everything stateful is great to stay on the host, and you're just sort of plumbing. You're trying to get the packet in and out. You want to make sure that you can avoid drops, avoid large latencies, avoid misrouting, avoid bottlenecks. If you look at sort of the FlexPipe that we did today, it was very focused on packet processing, flexible parsing, flexible modification, and then sort of the flexible type of control flow that you have in OpenFlow with multiple tables. But there's this whole other world of you have this fabric, you're very focused on the quality of that fabric. How does it deal with congestion? What is its latency characteristics? Not just low latency, but worst case latency. These are the types of things that you start to think about once you have a flexible forwarding and you can handle any sort of tag that's coming off the host, any sort of service tag that the host is using to do sequencing. Now you want to focus on, okay, I want to make a forwarding interconnect that the host can sort of forget about. It's just always there. It's always just a always available connection that doesn't have a lot of hiccups.
Yeah, no, that seems definitely like one way things could go. I think another question, of course, with software is you could imagine the hosts doing things at the edge, tagging packets, just treating the network as sort of an interconnect based on these tags, as you say.
Right.
And another place for hosts is like in the network itself, right? So another thing that kind of didn't really exist, when FlexPipe started, as we know, is things like service chaining, right? So you could imagine boxes sitting in the middle of the network in addition to, the end host doing tagging and other things at the edge. So, what kind of role do you see? Like, what kind of splits do you see in the network itself? Like, in terms of where are these boxes going to sit? Are they, you could imagine them, being all over the place. Like, one at every switch location across the network. One, how do you see the whole placement of software switches or software middle boxes, if you will, going?
Well, I think certainly if I was building a network, I wouldn't want to have to decide where my box has to sit. I'd kind of want to just let some other person decide where the boxes need to be placed and how they need to be wired. And that's based on their physical locality. And I'd like to virtually, if I need this frame to go through box A, box A, box C, I want to do that in software, and that's where the service chaining is coming from. And that's going to potentially break up some of these specialized boxes that were requiring you to push packets through them specially, and be able to control that virtually. And I see that being really compelling. So it's very likely that people will have their way. That's what people want. They just want their hardware to look very uniform, and ideally get rid of these boxes, because the box problem is once you have one box and you need one extra flow more than that box can support, you're stuck. Now you got to go buy another box. You got to rewire everything, and this is what NFV is promising, or service chaining is promising, is we can sort of smooth out that growth curve of how much middle box logic do I need. If I can just do it all virtually and use the same hardware for the middle box that I do my application, then that's a big win.
Yeah, no, I see like a really nice kind of substrate there, where basically, as you put it, the kind of everything is uniform, if you will, and you don't, as a network designer and operator, you don't have to worry about what box that is, because they all kind of like do similar things, and then if you run out of space, you just drop another one in. Is that kind of the idea?
Yeah, I think that's the nirvana. Yeah, if you can keep everything uniform, then it doesn't really matter what function. You just buy boxes, you just buy servers, and your workload will determine how many servers you need to get your job done. So
yeah, how far away are we from that? I mean, on the one hand, there's like a ton of legacy deployed equipment. On the other hand, like certain kinds of networks have really short upgrade cycles, or relatively short. So, do you think we'll ever reach this nirvana? Both in terms of, I mean, one is like, do you think we're getting close in terms of design, or that's one, is how close are we in terms of design, and the other is like logistically, or deployment wise, do you think we'll ever get there?
Well, I think some people are already there. I think some of the big guys who have money to spend and are motivated to make their make their operations very low cost. If they need this type of function, I'm not going to go out and buy middle boxes. So it's how do you make that more broadly available? And I think the middle box vendors are seeing this as well, and they're trying to evolve towards it because they have a lot of value in that box. And historically, they've just been wrapping their value in metal, but the value is still in the box, and there's no reason why that couldn't move to a software environment. But for them, it's sort of what do you lose from leaving the box? And that's again where the fabric might come into play. If the fabric can provide some of the value that you had in a controlled system, and you can get that same type of value in a standard network, again, that's another place where there's innovation to be had. Where you might just have a standard network, but if that network can give that middle box function some of the functionality that it had when it was a controlled system, that's a big deal.
That's interesting. You might see a lot of these, as you put it, like these companies that are selling things wrapped in metal just become pure software companies or something like that, right? Like here's the software and it could be dropped on any one of these uniform boxes, as you might say. That might be one direction, you think?
Yeah, it's possible. It's kind of hard as a sometimes it's just if you're a hardware company, selling software is hard. I work at a hardware company, so but yeah, that's the challenge at hand. It's sort of if you feel it's inevitable, then you have to go do it to keep going.
Yeah, you referenced sort of being a hardware company, but of course also Intel has these other interesting projects like RouteBricks, for example, which is like a pure, I guess you might say pure software router in the sense that it's a cluster of servers that will do to high-speed forwarding, and then you've got complete programmability in some sense because all of your decisions are being made in software. How do you see a system like RouteBricks fitting into the network? Particularly with respect to, with the FlexPipe chipset out there, do you see that there are going to be switches with the FlexPipe chipset and then some RouteBricks routers in there? Do you think? How do you see that playing out?
Yeah, I think the RouteBricks application is just one example of what you can do, in a software data plane. And RouteBricks uses a tool that we call the DPDK. It's the Data Plane Developers Kit. And what that allows you to do is take your software data plane and accelerate it using the IA instruction set underneath. And so you can move your packets in and out of that box a lot faster if you use DPDK rather than if you just use the standard Linux kernel. And these types of applications. Routing is one thing that you can do, but it's one of the simplest things that people want to do on these software platforms, on these server-based platforms. So this development kit really, accelerates that work. Whatever your, go back to those hardware vendors, whatever their value add is, they don't really, they don't want to spend a lot of time optimizing the packets in and out. They can leverage what Intel has done and just focus on their application. And so RouteBricks is our way to experiment and understand the requirements of that type of system. But we have a lot of customers doing very similar things, but they have a pipeline that's much more complicated than just scalable routing. Scalable routing, don't get me wrong, is also a hard nut to crack. But there's a lot of applications that you can do on these server-based platforms.
That's really interesting. Actually, that clears up a lot of things because you could sort of then just sort of view RouteBricks as a demonstration application of what could be done on a server-based platform at really high speeds.
Right. Yeah, you can think of it like that. And certainly, if you took RouteBricks and combined it with FlexPipe, that'd be another great demonstration of how you can integrate something happening on the server with something that's happening in the fabric and let them work together, and trade off their very different strengths,
Yeah, that's really interesting. So on one sense, you've got servers with this DPDK architecture running on the host, and then you've got switches with FlexPipe in the network. And there's some I guess there's some relationship between the two. It seems like. Do you see specific things where one could take advantage of the other, or vice versa?
Yeah, I think so. I think ASICs have their place, but the focus is how do we make that Intel architecture server platform the best platform for doing forwarding inside the network, and how to take network functions and put them on that platform. That's really the focus. But we think that having Fabric be a part of that, gives you a special advantage. If you can, again, we have a special development kit just to get the packets in and out of that server. And so we want to be able to focus on that I/O and have make sure the I/O isn't the problem. The bottleneck should be in the compute and the function that you're trying to, that where all the value is.
Yeah, I wanted to just dive in a little bit to the design of FlexPipe itself. So, I mean, first, I asked a couple questions at the beginning, like how did you just decide the set of actions and so forth. But also, what about layout? You had particular decisions that you needed to make when kind of laying out the processing pipeline and so forth. That ask some more specific questions about that in a minute. But for example, like a protocol that requires matching on two fields, it could be implemented as two tables in sequence, right? Each matching on a single field, or it could be implemented as a single table containing both fields, and you do some kind of cross products there. So that would be like one example where you have to make a layout kind of decision. But is that something that you faced, and what other kinds of layout decisions did you need to make when designing the architecture?
Well, I think that one thing we tried to focus on in the P4 paper was the control flow of the matching, right? To understand the logic that the application is going through when you're trying to process this packet. So you could think of maybe the logic of the application is going to do one lookup, come to some result, and then want to use that same result farther down the line in some other process that might have been created by some other application. And having that sort of serialized operation in your pipeline is sometimes really useful. Because it would be nice to be able to segment some of these functions in a single pipeline, so that one application can be programming one table and another application can be programming the other table. They don't necessarily need to be synced together, and that I think is really useful. But what we also determined in the P4 paper is that you don't necessarily have to have your hardware match that exactly. So if you determine that in your application you need two tables, but your hardware only has one table, something that something like an open vSwitch would do is just take the Cartesian product of the two tables, flatten them, and so luckily you can always stick something into a really big flat table, but it's not very efficient, and so from our standpoint, we wanted to make sure that you could break up these tables in the same pipeline without having to flatten them, without having to make large expansions of the table set, just because you couldn't do that serialized lookup.
Mm-hmm. Yeah, you mentioned P4 just briefly, and I wanted to ask one question about that. I mean, it seems like there's that's a language that would basically allow you to kind of define some properties of the underlying target hardware in terms of layout of tables and pipelines and so forth. What kind of factor, presumably that's a language, and then you'd need some sort of compiler that would consider various constraints of the underlying target and make decisions. I mean, what do you think that compiler is going to most need to consider? From going from a high-level language describing the layout to the actual, or describing the functions to the actual layout. I mean, is it power, area, latency, some combination of these things? Is that something that the designer or the programmer is going to have to specify, or do you think there's some sort of general set of axioms that may apply?
Yeah, it's unclear. It depends on the hardware. Our hardware, it is sort of there really isn't a power latency trade-off that you have when you use new features. So it's very efficient in that way, and it's very deterministic in terms of its behavior. But other designs might not be that way. They might, if you turn on one feature, it may completely change the behavior of that device. That's going to be a challenge for compilers. It's sort of I was running great, and then I added this new function that called this special action, and now I've lost a bunch of performance, or the box is running really hot, or those types of things. It's going to be challenging for compilers. So I can't imagine. I would imagine actually that a lot of the early compilers for this type of language might come from the vendor themselves to say, here is here is something that's been put out there in the community, and this is how I match to that compiler, and this is sort of how you can use it. But ideally, ideally there would be an open source compiler that would just be able to handle a lot of different hardwares, and that's certainly from my perspective that's sort of nirvana. But initially, there's so much knowledge that you need to know about the system that it has to sort of come from us. But it sort of influences our process too. So once these compilers exist, you'll start making less trade-offs that are hard for the compiler to grok. If it's maybe I won't make that hardware trade-off in the future because I know that it's going to cause the compiler all sorts of headaches, and it's going to be hard to express into the higher level of abstraction. So I think it will definitely impact our future devices if this type of thing sort of would emerge.
Mm-hmm. Actually, another thing that before we kind of chat a little bit more about FlexPipe, I wanted to ask you. You mentioned that a little bit of the design of FlexPipe was a little bit of the design of your layout decisions was somewhat motivated by things that you were thinking about when you did P4, which kind of led me to think, in what sense does the language drive the hardware design, and in what sense does the hardware drive the language design? Is there sort of a co-design going on there, or how do you think that interplay works?
Well, I think when we designed FlexPipe, there was no P4, but when we designed it, we had this sort of overarching goal that we wanted the pipeline to be very deterministic. So we didn't want, because it was so flexible, we didn't want you to go and enable some feature that that was part of the hardware spec, but then have the hardware behave really differently. We wanted the latency to be consistent. We wanted the performance to be consistent. Power, all of that to be the same, so that you sort of felt free to program it the way that you needed. That's our architecture. And a different architecture, if you don't have that, then it's very hard for the compiler. Basically, the compiler will say, I can't turn that feature on because I can't predict how this box is going to behave when I have it on. And so that's where I think the compiler really influences things, where you may in your future design say, you know what, the compiler wants this, people are using this feature, the compiler exposes it, I better make sure that it's performant and that it's not an exception case. That's where I think that's where the loop comes in, because when you're designing this hardware, inevitably you come up and say, well, either this didn't work the way I thought, or it's going to just take too long for me to do this right. So do I do it not exactly the way that I'd like? And I think you'll take that. You'll take a harder look at that when you know that eventually this feature will be exposed in a compiler and can be used in a lot of different ways. Right.
Mm-hmm. Mm-hmm. Yeah, it seems like there are a lot of sort of interesting open questions there in sort of the design of whatever this compiler eventually becomes.
if when, yeah, exactly.
Yeah. I mean, where do you think I guess you mentioned if, right? So where do you think that compiler is going to come from? Do you think that's are those is that an industry question? Is that something that researchers should be working on? If the latter, what do you think are the hard problems there? I mean, you mentioned some already, but
Yeah, no, I think,
Do you think that there's some that, in particular, that researchers should focus on?
yeah, I think it's a really interesting research problem to see if you can make a compiler that could work on lots of different hardwares. Uh, and could, maybe you focus on just kind of the least common denominator, uh, and be able to take, what would be cool in P4 is to be able to take the intention of the application or the programmer of the network, take that stated intent and put it into hardware. And you know, you're not always going to be successful in getting it all in there. And so how do you report that back and say, well, I got your program in there, but when you go over this number of rules or when you do this particular operation, it's going to have this performance. And what all you're really doing is trying to replicate the environment that you have on the host, right? On the host, it will always compile, it'll always run, it just might not run very fast. And this the new I guess challenge that you have on the switch is that variance in speed can be really big. So that's the challenge. So maybe the answer is just move everything into software, like we said in Nirvana. Just everything should just be software, and maybe the network shouldn't be programmable. That's one answer. But having a compiler that can do this type of thing on a network device would be really interesting.
Mhm. Do you think, I guess one more question about the compiler, do you think that the right answer is like, oh, it always runs, but sometimes it might just run super slowly, or do you think the answer might be, oops, sorry, can't do it, like, compile failed, try again, almost like a compile time fail?
Right. I think it should always run. That's
Uh-huh.
what happens on a host. It should always run.
Right.
It might run. It might run super slow. Or if you have hosts nearby, maybe you could just go run on a host somewhere.
Mhm.
So it's very easy for the ASIC to say, I can't do this, so I'm going to go and send it somewhere else. So they're I absolutely think that this compiler would have to take that into account and look at it more of at a system level and say, well, I can't do this, but I might have some other pipeline or some other method to get it done. And maybe for a lot of applications that's acceptable. Your sort of standard forwarding is very high performance, but there's some exception cases. There's some control plane functions that you'd happily run as slow as you can, but you want to use the same interface that you did for the bread and butter data path. So it would be really nice if the programmer could just say, this is what I want. This is a description of my system. This is how I want you to forward it. And tell me what pieces might run slow, and I either don't care or I'll use that information to better improve my program in the future.
Mhm. You mentioned, like with the compiler, the holy grail or something or the nirvana, as you say, would be, compiling to multiple target architectures. I imagine FlexPipe would obviously be one of them. But what other chip architectures are out there that compiler designers, should they appear, what should they be considering?
Well, they should always consider x86.
Of course.
And maybe that's where they should start.
Right.
You could imagine, let's take a compiler that runs x86, and if I could maybe take parts of that function and push it onto a different pipeline that's FlexPipe, that might be one approach to the compiler. Or you could flip it around and take it the other direction and say, well, I want to start with a compiler that's focused on a particular pipeline, like the logical architecture we had in P4, and then the things that don't fit, I will put into a generic x86 pipeline. Those are certainly two ways you could do it, but I think you sort of have to incorporate somewhere a software data plane. And we sort of see that in scores with SDN, is that SDN sort of looked at the market in general looked at all the data planes and said, you know what, for me to add my value and for my startup to make lots of money, I need to have ultimate flexibility, and so a lot of that landed on vSwitches.
Mhm. What about there's some other, I guess, chipset architectures being developed as well, like this RMT
Mhm.
architecture. I was wondering if you could sort of compare and contrast FlexPipe to RMT a little bit. Like, what do you think the major differences are between those two chip designs? Uh, and actually, I guess maybe this isn't a question for you, but FlexPipe came first, right? So, like, why do you think RMT even came about? Like, given that FlexPipe was already, it already existed. Do you think there's a need for both of these? Like, what are the major differences? And do you think they're complementary? Do you think, what's the lay of the land here?
I think they're really similar. I mean, I think that RMT was inspired by FlexPipe in some
Hmm.
respects, at least as an existence proof. And those, I'm sure they'll argue with that. But they both have programmable parsing, very similar programmable parsing functions. They both have programmable modifications. Uh, they both are sort of flexible in terms of how you match, whether it's TCAM or longest prefix or exact match. The main difference I would say is that uh, you know the FlexPipe was designed for that determinism. We want to have the pipeline behave exactly the same every time, and even down to latency. And so that means that a lot of our computation happens in parallel, so that you can do a bunch of matches all at the same time, and then gather a result, and then use that for your forwarding. While RMT is much more serial, and it's certainly a trade-off in terms of serial has a lot more power. I just mentioned that example before, where you might want to have one table come up with a result, and then the result of that table can be looked up in the next table. And so I would say that RMT is much more serial. FlexPipe is a bit more parallel, but they have a lot of similarities. And I think that they're similar enough that if you had to go and make a compiler that could do both, I mean, there are probably two chipsets that are probably a good example because they are similar enough without being exactly the same.
Hmm. I see. Yeah. So those might be two targets to consider as well for a compiler designer.
Right.
Um, yeah. What do you think are the major differences that result from the decisions? I mean, you mentioned RMT being more serial, FlexPipe being a little more parallel. I mean, do you think there are like performance implications here, or other implications for the programmer even? I mean, what do you think the upshot is with the differences?
Uh, it's really the difference between serial and parallel would just mean differences in control flow. So
Hmm.
if you have a lot of parallel functions, you have a function for QoS, you have a function for forwarding, a function for monitoring, a function for security. All four of those can run in parallel. But if you have to serialize them, that might have a performance implication. But if you have a function that is going to look at a tag and then create some metadata, and then look at that metadata and look at another part of the frame, and then create some more metadata for a later, ACL or flow match, that can be very powerful too, the serialization. So I think you know what we end up doing is just sort of influencing each other. Later later flex pipes might be more serial, and later RMTs might have less of a much more deterministic performance. That's most likely, I think, the result. But if I was writing a compiler, it'd be fairly straightforward to switch between the two because they both have. It's really the lowest common denominator between the two is pretty large, and it's that programmable parsing that is a big deal. They're both kind of protocol independent. They're not
Hmm.
they're not required to only match on sort of the tuple that's defined in an early OpenFlow spec.
Hmm. So yeah,
Uh,
so I mean, you mentioned the programmable packet parser as kind of being the big deal. It seems like there are a lot of these chips that kind of have that flavor where you can sort of match on arbitrary portions of the packet,
right.
bits in the packet header and so forth. Are there things that are kind of specific to FlexPipe there as far as the programmable parser, or things you mentioned that RMT was kind of inspired by FlexPipe? Are there differences between the parsers that are noteworthy, or think they're close enough?
I think they're pretty close. There are other parsers that are very, very fixed, and that's where the big difference comes. They're pretty similar in that they're sort of kind of state machine based. You kind of look at some of the bytes, you make some decision, and you roll forward in the header to figure out what your next function is. So from that standpoint, they're pretty similar.
Got it. Cool. I wanted to just close with maybe, I don't know if it's controversial, but certainly coming back to the hardware-software question a little bit. Maybe just talking a little bit about middle of the road, right? So there's certainly on one hand there's servers and DPDK and x86, and on the other hand there's FlexPipe and switches and so forth. And somewhere in the middle, maybe there's programmable hardware like FPGAs and things like that. I mean, certain switch vendors are known to ship line cards with FPGAs on them for experimental purposes, to test things out before the, in between development cycles. I'm wondering, do you see a role for this kind of programmable hardware in the network at all, or is it just all one side or the other?
No, I definitely do, especially at the edge of the network, close to the x86. If you had an FPGA sort of hanging off the processor, or maybe an FPGA hanging off a switch that was also connected to a processor, there's a lot of interesting things that you can do at that edge. No, we run into FPGAs all the time. It's an interesting place it's a great playground, and it gives you that trade-off between. It's a much better trade-off between flexibility and performance. So I think there's absolutely a place for that, and to the point where you asked about what's a good platform for these compilers. If your compiler had sort of a generic x86 forwarding pipeline and could take advantage of some FPGA, that would also be a really interesting combination.
Interesting. So you think there's maybe even a place for it in production, not just sort of in a development cycle sense, or?
Yeah, absolutely. And there are definitely customers in production that use FPGAs in sort of in that realm that I just described. So you're not as cost sensitive certainly as a big data center, but there's when there's a certain performance metric that absolutely counts, let's say latency, FPGA is a good tool.
Cool. Well, thanks. This has been really exciting, really interesting for me as well. So thanks a lot for your time. I hope the students in the course also get a lot out of it too. We're going to be covering your architecture in the course as well, so it'll be a lot of fun to get your. It'll be very useful to have your perspective. So it's great. Thanks a lot.
Great. Thanks a lot. Thank you.
Yeah. Thanks.